So I want to talk about how we can use integrals to find volumes. So I have drawn like a vase-ish shape, and if we wanted to find the volume of this, right, there's not a straightforward formula for it. So what we do is we're going to slice it sort of perpendicular to the axis of symmetry. So here would be my axis of symmetry. So we'll just do these little slices, and then we'll find this area of the, right, a cross section. So, and then we'll add them up. So we'll add up the areas times their little thickness, right? So here's the thickness. And then the area. And that'll give us this little slice of volume. And then we'll add up all of those slices, and it'll give us the total thickness or the total volume of that vase shape. So what we know from previous chapters in calculus, when we have this, right, the idea is we go from the sum of the area times the thickness to the integral of that cross-sectional area. And then that thickness, right, it's the little delta y if it's oriented this way, and then it becomes a dy. If we rotate this so that it's, right, if we have a shape that's oriented horizontally, then we would have an area dx. Okay. Something to keep in mind when you set up your integral, if you are integrating with respect to y, then make sure your limits of integration are also y values. So the lower y to the upper y. Same thing here, if you're integrating with respect to x, it's the lower x and the upper x. Okay. So what we're going to do is we're going to use this idea, so you can see it in play, to derive the formula for the volume of a cone. Right, so we know the formula v equals 1/3 pi r squared h, and I've drawn a cone here and I've oriented it along the y-axis. So what we're going to do then is we're going to grab a slice in the middle, an arbitrary slice, and give it a little thickness so that we can see it. And then what we want to write is the area times the thickness. So I already see, since I've drawn my little circle in there, that my thickness is a dy. So now I just have to find the area of the circle. And you don't have to start right all the way in with something in terms of y. Let's just start basic. So it's the area of a circle, right? So the area of a circle, pi r squared dy. And now we need to figure out what r is in terms of y, but we don't even have to go that far. So r, right, the radius of that circle is the same as the x value, right, on our axis here. So now I have pi x squared dy. So I'm getting closer, but I need that x to be a y so that I can actually, right, do the integral. So now I need a relationship between x and y. And there are a bunch of ways you can go about it, believe it or not. So you could either do similar triangles, or you could do the equation of the line. And I think I'm going to do similar triangles. So let's find the similar triangle. So so imagine slicing this down, right, so that we just get a triangular shape. Come down here. So here's my r. And then at some point, right, we have an x. So here's this circle in the middle, and there's x. And this whole thing is h. Now here's where it gets a little bit tricky. So when we're looking at our points on the graph, it's this little part down here that's your y, but the similar triangle part is up here. So this region at the top is h minus y. So then my similar triangle, so h is to r as h minus y is to x. Okay. So remember, we're trying to get x in terms of y. So let's see, let's cross multiply, do a little algebra there. So hx equals r times h minus y. X equals r over h times h minus y. And then we need to square it. So let's go ahead and I'll come back up here. So pi x, so let's go ahead and square it as it comes in. So r squared over h squared, and then h minus y squared dy. So let's see, pi can come out. Integral r squared over h squared, expand h squared minus 2hy plus y squared dy, pi r squared, oh, let's take the r squared through. So r squared, the h squareds will cancel, minus 2r squared y over h. One of the h's will cancel, and then plus r squared y squared over h squared dy. Okay, so integrating with respect to y, all the other letters are constants. So now we have pi times r squared y minus 2r squared over h, let's see, y squared over 2, plus r squared y cubed over 3h squared. And then, oh, what were my limits of integration? So, right, it was dy. What does y go between? Right, so y starts at 0. Think of where your circles start. They start down here where y equals 0, and they stop at the top. So it starts at 0, and it stops when y gets to h. So we're evaluating y's between 0 and h. So we can go ahead and plug those in, and we get pi. Okay, so I should have done this before, and it's been bothering me. So that r squared, go ahead and bring it out to the front because it's in all of our terms. And then I have, so y gets evaluated at h. So I'll get h minus, let's see, that guy's out, these guys canceled. I get h squared over h. And then in my last term, r squared, remember, got factored out. Y gets evaluated at h. H cubed over 3h squared. Almost there. Oh, and then the 0, but each of them has a y in it, so the minus 0 goes away. So now I've got pi r squared. Let's see, cancel, cancel, and then h minus h, so that's 0. So all that's left inside those brackets is an h cubed over 3h squared. Oh, let's get rid of those h's. So this one and that one. And there we have it. Pi r squared h. There's one h left on the top and a 3 on the bottom, which is exactly our volume formula.